Hello, Physics 1. Mr. Janowski here. So here is the first part of the slides. I'm going to try to go through them pretty quickly. I've been making these videos for other classes so far, and I always try to make them quick, and they end up being too long. So I'm going to try to go quickly through this. All right, so remember last week we took the mechanics baseline assessment, and the question is, how do you think you did? And in class, I asked everyone, do you think you got a 90, an 80, a 70? Did you pass? And then I warned everyone that this test is not at all like my test. This is a rather mean and unfair test designed by a group of physics teachers whose sole goal is to point out the strong misconceptions that people have about physics before they take physics for the first time. So no one does well on this test. Don't be alarmed. So yeah, more words. And then we get to the results of the test, which I'll go through kind of quickly. So yeah, the average out of all of the physics students at Charter Arts who took this year, which I believe was 72 students, was 19%. The very highest score was 47%, and a couple of people this year did get 0 out of 30 correct. That doesn't happen every year, but it has happened before. And it's not surprising, and it doesn't mean you'll do poorly in physics, and it doesn't mean that you're unintelligent. This is not a test that can predict either of those things. This is only a test that tells you how strong your misconceptions in physics are. So then I break down the 30 questions into different categories, and year after year, the categories that people have the most trouble in are Newton's third law and force motion. So this is useful information to me because it tells me what areas I need to really stress, what misconceptions I need to look at when we cover these topics. So this year's scores compared to last year's scores, again, this year our average was 19%. Last year it was 22%. They beat you by a little bit. Don't take it personally. But yeah, you'll see the same trend. The lowest scores this year as last year were in Newton's third law and in force motion. And then there were two questions this year. Didn't mean to click back. There were two questions this year where only a very small number of people got the answer correct, and a very large number of people picked a particular wrong answer, meaning there's a particular misconception about these things that a lot of you have. So when we get to these topics, I know what these topics are. I'm not allowed to tell you. It's a weird test, and there are rules about it. But I know what these topics are. I know what these misconceptions are. So when we get to them, I'll know what to do. And then we begin chapters 2 and 3. So the first quote unquote chapter that we'll do is actually 2 chapters. It's 2 and 3. We'll do them kind of quickly. And at the end of chapters 2 and 3, there will be a big quiz. It won't be a test. It will be a big quiz. Different than my tests. So yeah, first we define a force. A force is a push or a pull. A force is always required to change an object's state of motion. Change is the important idea. Forces change motion, which means if the object is at rest, it will stay at rest unless it is acted upon by a non-zero total force. And if the object is in motion, it will stay in motion, and its motion won't change unless it is acted upon by a non-zero total force. So that may sound very logical, but please be aware that deep down in your bones, you don't really believe this. Because if you did believe this and you accepted this and you had the right idea about this, then the scores about force motion on the mechanics baseline assessment would have been much higher. But don't feel bad. You're not the only ones who have this misconception. Everyone nationwide who's taking physics for the first time have these same misconceptions. And famously, Aristotle, the ancient Greek philosopher slash sort of scientist-ish, he also had these misconceptions about forces. So as smart as he was, allegedly, he didn't understand what forces did and how they affected motion. So the symbol for force will almost always be a capital letter F. So that's good. That makes sense. It won't always be that way this year, but it's usually always a capital letter F. Sometimes, really often, with a subscript. So a subscript, sub means below, is going to be the little letter next to the F here. So the first one we have is F sub G, or F sub lowercase g. So a subscript is like an adjective. It's telling you more precisely what the thing is. So this is not F times little g. Sometimes algebra looks that way, but that's not what this is. This is F sub little g. So this is the force due to gravity, more commonly called weight. So yeah, you're experiencing this force right now if you're on the Earth. There's also a force called the normal force, which is written as F sub capital N. I'll tell you more about the normal force in a couple of slides. And introducing Alice, Billy, Charlie, and Denise. These are 4 characters who will appear in many of our physics problems. So maybe we'll have a problem where all 4 of them are exerting different forces on an object. And to keep it straight when we're doing the math, which one's which, we're going to use subscripts. So Alice would be, the force due to Alice would be F sub A, et cetera, et cetera. And the most common unit of force that we're going to use this year is the Newton, written as a capital N. So the rule is if you're writing out the word for the unit, you use a lowercase n, and when you're writing out just the shorthand, you would use capital N. So for example, if Alice is exerting a 100 Newton force, we would say that F sub A is equal to 100 capital N. So common forces. Yeah, there's weight. So this is the force due to gravity between the mass could be anything, and usually the Earth. So unless otherwise stated, you can assume that we're doing our problems on the Earth. There's a force called tension, which you might write as F sub T or just T sometimes. So here is a force not being a capital F. This is the force due to a string, a rope, a chain, or the like. So for example, looking at these first 2 forces, if we were doing a physics problem that had the elevator in the elevator shaft, well, that thing has mass, which means there's a force due to gravity pulling it down towards the Earth. But there's also a cable on top of that, and that cable has tension in it, and that is exerting the force that's pulling the elevator car upwards. So friction. You might think friction would be F sub F, but it's actually either F sub K or F sub S. This is the resistance between objects across each other. So there are 2 basic types of friction. There's kinetic friction, which is when the surfaces are moving relative to each other. So if you put your hands together and rub them back and forth, that is going to be kinetic friction because the surfaces, your hands, are moving relative to each other. If you put your hands together and you're trying to move them past each other, but you're squeezing them together so hard that they can't actually move, well, then the surfaces aren't moving relative to each other, and that kind of friction is called static friction. So kinetic, kinema, cinema, all these things means motion, and static means not motion. The things aren't moving relative to each other. And then now the normal force, F sub n. Whenever 2 objects press against each other, they exert a normal force on each other. So for example, right now the Earth is pulling you downwards, and the reason you are not falling down towards the center of the Earth is because you're getting a normal force from the chair that you're sitting in. So yeah, that's normal force. And normal does not mean, in this context, does not mean regular or ordinary or anything like that. It's the mathematical meaning of normal, which is perpendicular. So if you draw a line between wherever the 2 surfaces are touching and you draw the tangent line there, the normal force is acting perpendicular to that tangent line. So we call it a normal force. There will be lots and lots of normal forces, and normal means perpendicular. So there are 2 types of quantities. The quantities this year will either be scalars, which means they have a magnitude, which is just a mathematical way of saying size only, or they will be vectors, which have a magnitude and a direction. So forces are vectors because they have magnitude and direction. You can have a 100 Newton force directed in any direction. Could be up, down, left, right, east, north, 30 degrees above the horizontal, etc. So forces have direction, which make them vectors. Examples of things that don't have direction and are therefore scalars are age. So I am 43 years old. I am not 43 years old north. There's no such thing as that. That doesn't make any sense. Temperature. So maybe it's 70 degrees outside right now. It's not 70 degrees to the left. That ain't a thing. Yeah. So that's the difference between scalars and vectors. So every time we learn a new quantity this year, I'll give you a slide like this, where we learn the name of the quantity, in this case force, the symbol, which is usually capital F, the units, which are newtons, capital N for Newton, and is this thing a scalar or a vector? This thing is a vector. Forces have magnitude and direction, therefore they are vectors. So mechanical equilibrium. So I know I'm ripping through this, but again, I'm trying to make these slides short. I feel like if I don't make these slides nice and bite-sized, then no one will be able to watch them and they'll be of no use to anyone. So, mechanical equilibrium is a state wherein no physical changes occur. It is a state of steadiness or balance. So, there are some misconceptions about this. It's steadiness, but that doesn't mean that there's a lack of motion. So, mechanical equilibrium does not necessarily mean that the object is not in motion. You can be in motion and still be in mechanical equilibrium. So, what it does mean is that the object's motion is not changing. So if it's moving already, it's going to keep moving, straight line, constant speed. That's mechanical equilibrium. And if it's not moving and it continues not to move, well, its lack of motion is not changing. So that is also mechanical equilibrium. So yeah, forces change motion, but mechanical equilibrium does not necessarily mean that there are no forces on the object. You can have forces on an object and still be in mechanical equilibrium. What it means is that there is no net force on the object. And I'll talk about net on the next slide. So the equilibrium rule. Whenever the net force on an object is zero, the object is in mechanical equilibrium. And the flip of that is also true. If the object is in mechanical equilibrium, then you know for a fact that there is no net force on the object. The net force on that object is zero. So here's the idea of net. Net force is equal to F sub net. This is one way to write it. This is not my favorite way to write it. More on that in a slide or two. But often there will be situations where we'll have more than one force acting on an object, and we'll need to figure out what is the net force. So what does net mean in this context? So imagine you want to start a lemonade stand. You buy $5 worth of lemons. You buy $1 worth of sugar. You get all the other supplies you need for free. Maybe mom and dad lend you the other supplies. And you go out that day and you sell $20 of lemonade. So how much did you net? Well, you didn't net 5 plus 1 plus 20 equals 26, because that's not how money and math and accounting work. You netted $14. So net is the total. It's the sum, but you have to add them up in a particular way. So the fact that $5 and $1, those were both costs and those were going out, those were away from you. That's why I added them this way. I still use pluses, but I wrote them this kind of funny way. So these have minus signs in front of them. So yeah, minus 5 plus minus 1 plus 20 equals 14. So yeah, that is your net profit. So same idea with forces. We're going to add the numbers up, but we're going to be sure that we respect which way they're going. So net force is equal to F sub net is equal to this funny symbol F. So what is this funny symbol? This funny symbol is the capital Greek letter sigma. So in math and physics, sigma means sum. So sigma is a Greek letter S, so it means, S for sum. That's what this means. And in math and physics, we never use capital sigma as a variable. Capital sigma, it's got this special job. We reserve it just for this. It means sum. So if we look at the top of the slide, the title, sigma F, this is not sigma times F, even though algebra-wise it kind of looks that way. You just have to know when you see a sigma, that means the sum of the things. So when we start setting up force problems, it's going to make the most sense to write sigma F. So I would rather write sigma F than F sub net. And that's the way I'm going to do it throughout the year. And I encourage you to do it that way throughout the year too. This idea of sigma is going to be important. So for example, let's say that we have some object, and Alice is pulling to the left with 20 newtons, Billy is pulling to the left with 10 newtons, and Charlie is pulling to the right with 18 newtons. We want to know what is the net force. What is sigma F on this thing? So you could write it like this. Sigma F, the sum of the forces, is the force of Alice plus the force of Billy plus the force of Charlie. And then when you go to the actual numbers, again, you have to respect which way the numbers are going. So the convention we're going to use throughout the year, the convention everyone uses in physics, is if the thing is going left, you make it negative. If it's going right, you make it positive. If it's going down, it's negative. If it's going up, it's positive. So when I add these forces together, I have negative 20 newtons plus negative 10 newtons plus 18 newtons, and I end up with sigma F, the net force, is minus 12 newtons. And the fact that it's minus 12 newtons clearly implies to a physicist that it's going to the left. You could also write 12 newtons to the left. That would work as well. But other than that, you keep to the convention, and minus 12 newtons means it's either to the left or it's down. And the context here tells us it's to the left. So equilibrium for objects at rest. So we have a physics student sitting motionless in her seat. She is in equilibrium. So what forces are acting on her? There are two, or at least two important ones that we care about. There is a force due to gravity, which is her weight pulling down on her. And there is a normal force that she's getting from the chair pushing up on her. So we have forces acting on her. Neither one of these forces is zero, and forces change motion. So why isn't her motion changing? Why isn't she moving? Why is she still in mechanical equilibrium? The answer is because the sum of the forces on her is zero. These forces are canceling each other out. These forces happen to be equal and opposite. They're equal in magnitude and opposite in direction. So even though we have two non-zero forces on her, these forces are such that they exactly cancel each other out, and the sum of the forces, F sub net or sigma F, is equal to zero. So she is in mechanical equilibrium. So it can be harder to see mechanical equilibrium for objects in motion. You're going to have stronger misconceptions about this, most likely. So if the object is at rest and it just continues to be at rest, it is always in equilibrium. Because if there were a non-zero total force, a non-zero net force acting on that object, it would start to move. It has to. If you have objects that are already in motion and they're moving in a straight line and at a constant speed, then they are in a state of equilibrium. Straight line, constant speed, that's a phrase you'll use a lot in physics. It comes up a lot. So think of some objects you've seen move this way. So if you have a figure skater just coasting across the ice in a straight line, that figure skater is in equilibrium. So if you're skating and you're pumping your legs and you're gaining speed, you're not in equilibrium. If you're doing a hockey stop and you're slowing down, you're not in equilibrium. If you're turning, you're not in equilibrium. But if you get going and you just, go up on one foot and just gracefully cruise in a straight line, then you're in mechanical equilibrium. Now, you're not exactly in mechanical equilibrium because there are still little forces on you, but this happens a lot in physics, we say that they're negligible. So there's a tiny bit of air resistance, and there's a tiny bit of friction between your skate blade and the ice, but those forces are so small that we just pretend that they're not there. We have to do that a lot in physics. So if you're coasting on your bike across level ground, so you're not gaining speed or losing speed, you're just coasting, and you're going in a straight line, then you're in equilibrium. If you're pushing a couch at a constant speed across the living room, this is mechanical equilibrium. So there are going to be four forces on this couch at this point. There's gravity pulling it down. There's a normal force from the floor pushing it up. There's the force that you're applying on it, pushing it sideways. And there's another force, the force of kinetic friction, F sub k, pulling it back the other way, opposing your motion. But if you're pushing this couch with exactly the right amount of force and you're exactly canceling friction and the normal force from the floor is exactly canceling gravity, then you have no net force and therefore the couch is in mechanical equilibrium. So back to this idea of vectors. I know we're covering a lot. Sometime you will have vectors that are in the exact same or the exact opposite direction. These are very easy to add. If they're in the exact same direction, you just add them up. The vectors we have on this slide, they're in exact opposite directions. So the red one's bigger than the blue one. So let's imagine that these are two forces. When you add them together, you just take the small one and subtract it from the big one, and you're left with this one. This is called the resultant. The sum of two vectors is, you can either call it the sum, but there's a word for it. It's resultant. So yeah, in this case, parallel vectors or anti-parallel if they're in opposite directions, these are easy to add together. So sometimes you're going to have vectors at right angles. These are a little bit harder to add together. They're not the hardest, but they're a little bit harder. So for example, let's imagine that at this little point right here, we had some kind of mass, and maybe Alice is pulling with a force of 4 newtons to the east, and Billy is pulling with 3 newtons to the north. What do we get when we add these vectors? Perhaps somewhat surprisingly, the answer is 5 newtons at this angle, kind of to the northeast. You have to do trig to figure out exactly what the angle is. But yeah, welcome to physics. Sometimes 4 plus 3 equals 5, because now numbers are vectors and they have direction, and you have to pay attention to the direction. So it's weird. So who taught us how to do this stuff? Well, I mean, it could be Babiez or Mrs. Evans or someone in the math department, but originally it was Pythagoras. So yeah, this is a right triangle. This is a 3, 4, 5 right triangle. And we'll deal with this kind of thing later on in the year. And the last case is sometimes you will have to add vectors and they won't be parallel or anti-parallel. So they're not in the same direction or the exact opposite direction, and they won't be at right angles. They'll just be at what we call an arbitrary angle, which means just some other angle. So these are the hardest kinds to add together. So if you stick with physics and you take Physics 2 with me next year, we will learn how to add these things mathematically and come up with exact answers for the magnitude of the resulting vector and the angle and all of that stuff. But this year in Physics 1, when we see this kind of thing, we'll only do it graphically, which means we'll just draw it out and get a general idea of what's going on, but we don't get the actual number. So there are a couple ways to add vectors. One is the parallelogram rule. So if we were adding the red one to the blue one way you can do that graphically is copy the red one, put the copy up here, copy the blue one, put the copy over here, then go back to where you started and draw the diagonal across. And this is the way you add things with the parallelogram rule. And rectangles are a form of parallelogram. It's a specific kind, but it is technically a parallelogram. So that's how that works. The parallelogram rule, of course, also works if you're adding arbitrary vectors. This is also a parallelogram. So just copy the two vectors, build a parallelogram, draw the diagonal. And let me go back real quick just to emphasize one thing. So the final direction, this should make some kind of intuitive sense because we had one, let's imagine these vectors are forces. There are different kinds of vectors, but let's imagine that they're forces. So we had a force going to the east, and we had a force going to the north. So when we add those forces together, we should end up with something that's going kind of northeast or east-north. This is more east than north in this case. So yeah, that's why you should know that you get a vector going this way, and the arrowhead is going that way. And the arrowhead is not going the other way, and it's definitely not going down and to the right or up and to the left or northwest, And finally, the last way of adding vectors graphically is tip to tail. So this is the way I learned it originally. This is the way I still like it the most because tip to tail works if you're adding 2 vectors or 3 vectors or 4 or 5 or however many vectors. You can just keep adding them tip to tail. So let's imagine that we had a little object right here in the middle, and we've got 3 forces acting on it. So maybe this is force of Alice, force of Billy, force of Charlie. And we want to figure out, well, what's the net force? So what you do is you just grab any one of the vectors first. It doesn't even matter which one you started with. I started with the red one, but you could have started with any of them. And you follow that vector out, and then you go from the tip of that vector, and to that you attach the tail of any other vector. So I took the blue one, I slid it over here like this, and I attached the tail of the blue one to the tip of the red one. And then I had one vector left. So I went from the tip of the blue one, I grabbed the tail of the green one, moved it up here without changing its direction, and tacked it on right there. And that got me to this point. And then the last step that people like to forget is you have to go back to the beginning, and then you draw it to the end. So yeah, we had a vector going to the east, a smaller one to the northeast, and a slightly smaller one to the southwest. When you add them together, the vector you get is going in this direction. So a little bit north of east is how this one ended up. So for the next class, try to remember to bring a single playing card. You don't need the whole deck of cards, and a coin, preferably a penny. So if you don't have a deck of playing cards at home, you could use your student ID or a library card or some other card or an index card. But if possible, try to grab a playing card just so we're all doing the same thing together. And yeah, we'll do a little remote demonstration activity thing together. So quick review. This video is getting too long already, but we're almost done. So what are the 2 forces acting on this physics student? There's a normal force from the chair pushing up. We call that F sub n. And there's a force due to gravity, i.e. her weight, pulling her down. We call that F sub g. What is the difference between a scalar and a vector? Well, a scalar has one thing. A vector has 2 things. A scalar only has magnitude, which is the fancy way of saying size, whereas a vector has magnitude and direction. So size and direction. And we just learned 2 ways to add vectors. So what are the 2 ways? There's the parallelogram rule, or I could call it the parallelogram method, but I call it the rule because Some book called it the rule. And also the tip to tail. So these are the two ways of adding vectors. That's it for next time. No homework other than, if you can, bring a single playing card and a penny. Hopefully you found this helpful.